Good evening, everyone.
Evening, madam.
Good
Okay.
evening.
Yeah. Good evening. So today we'll be discussing we will continuing with the last class that we were studying about organometallic compounds. So, uh,
Good evening, ma'am. I have a doubt about semester exam, ma'am.
okay, what is your doubt?
Ma'am, in December 2024, semester 1 and 2 both will be held or only semester 1 will be held, ma'am?
Actually, regarding that, you can directly contact your coordinator, sir. And
Both will held.
okay.
Both will held. You will send the schedule second semester. Okay.
Sir, we can understand, sir.
Both will held. Both the semester will organize the class. Now first semester is going on. You must do the first semester class. You will send the second semester link also.
Okay, sir. Thank you, sir.
Any other questions? Okay. So we'll continue. So today we will be discussing, we'll continue with the organometallic compounds and their various classifications that we were discussing yesterday. So today we will start with the bivalent organometallic compounds and here. So we'll study the different bivalent organometallics of silicon, germanium, tin and lead. So bivalent, they have these particularly bivalent organometallics, they have been extensively studied and they are just an evolving group in research, and they are particularly they have been explored for to understand their reaction mechanisms, their structures and their bondings. So here we'll study a few of the very important organometallic bivalent compounds, and here you can see the preparation method. So we'll start discuss a few of the preparation methods. So here the first preparation method, it talks about pyrolysis. So we all know pyrolysis is a heating process, but at elevated temperatures. So mostly the temperatures is beyond 400 degrees centigrade. Plus pyrolysis is usually carried out in an inert atmosphere. That is, in pyrolysis, the atmosphere is devoid of oxygen. Plus the temperature should be high, and the heating is performed in a controlled chamber. So the pyrolysis, by the process of pyrolysis, the preparations of silanes has been performed, and silanes here they have been obtained by pyrolysis of silanes. Now if you look into equation 4.33, you can see that the temperature is kept above 200 degrees centigrade, and the pyrolysis has been performed on silanes, and that yields the bimetallics of silicon, that is these are called as silylene. Here it is given in equation 4.33. Other methods that has been here, it is represented in equation 4.34, and also in equation 4.35 you can see the temperature has been maintained at 300 degrees centigrade. So now in general these silylenes, they are analogous to carbines. We know here, if you look into this, they are analogous to carbons in nature, and they are given as SiR2. Now also, apart from pyrolysis, ring contraction reaction of cyclic polysilanes have been done in presence of HNu, that is light, and they have been known to form the silylenes, as here it is represented in equation 4.36. Here we can also see reductive elimination is also in process by which we can obtain the such compounds. Like the dehalogenation reactions, they also provide another route for the generating of this silylenes given by the equation. Here it is shown in figure 4.38. So there are various methods by these are the pyrolysis is one common method, and then comes the reductive elimination here, which is represented in equation 4.38. Further, if we go deeper, we can look into the equations 4.39 to 4.41. These reactions, they undergo the insertion reaction, or what we call it as the addition reactions, and they give different types of products, as here you can see the reactions here. Now one another type of reaction is called as metathesis reaction. Now we know metathesis is a type of chemical reaction which undergoes dynamics and there is an exchange of either atoms or functional groups between the two species. So this is most a equivalent symmetry type reaction, and this metathesis itself, it indicates an exchange of either atoms or functional groups when we consider the between the two reacting species. So here the simple alkyl or aryl stanylenes, they have been given as they are designated as SNR2, and they can be prepared by the following reactions given in equation 4.42 and 4.43. So from these equations we can generate the SNR2, that is the alkyl or aryl stanylenes. So here SN is present. Here you can look into these reactions and you can find out. So depending on the nature of the R that is attached, which might be a simple or a complex aryl or alkyl group, then we can look into the stereochemistry of the resulting organometallic compound. Now let us say, for example, we have this ligand CHSIMe3 whole 2. Then here in the formation, since this is a bulky ligand, here the reductive elimination and metathesis, when you look into this reaction in 4.45, you can see they are stable, they react to form stable and isolable subvalent organometallic derivatives of tin, which is here it is shown in 4.44 to 4.46. So these are some of the metathesis reactions of organo SN. Here in this scheme 4.1, we can see the different synthetic routes for the preparation of tin metallocycles. Depending on the type of the reagent and particular reaction parameters, different types of tin metallocycles have been obtained. Now when we look into this, the structure and bonding of these types of derivatives, the type of tin and lead derivatives, they are soluble in hexane, benzene or and ether. However, the analogous of germanium, they are less soluble and they are like more soluble in diethyl ether. However, when we talk about the lead derivative, it is highly explosive and it cannot be handled in normal air or atmosphere. So the ground state valence electronic configuration for germanium, tin and lead, they, that is mostly ns2 and np2. That is for germanium it is 4s2 4p2, for tin it is 5s2 5p2, and in lead it is 6s2 6p2. Here it is represented here in diagrammatically, and we know that these elements, they form bivalent organometallics by the bonding with the help of these two unpaired electrons. So the sp2 hybridization of the valence shell electrons here, that is represented here in figure 4.23, it happens where M is the germanium, tin or lead. So thus the SPX and PY hybrid orbitals, they form two covalent bonds. So here in figure 4.23 we can see the sp2 hybrid orbitals of the bivalent organometallics. So when we move into the other group elements, the bivalent derivatives, they both have an empty p orbital and also an empty orbital that contains a lone pair of electrons. So as a result of this, both the types of Lewis acid and Lewis base type behavior is expected when we move towards the fourth main group type elements. So here in scheme 4.2, the chemistry of the bivalent group of the group 4 metals have been, here it is explained using this as a typical example. So in this, here in scheme 4.2, some of the typical reactions of bivalent organometallic of tin, here SnR2, it has been shown. These are some of the particular and peculiar reactions that occur. So now, although we know that this tin complex is monomeric in cyclohexane solution, when we look into the crystal structure, a dimeric structure was obtained from the crystal structure. So what happens here is, the normally it exists in cyclohexane solution. It exists as a monomer. It was isolated as a monomer, but when the X-ray structure crystallography was studied, it was found that it exists as a dimer. And further analysis of the structure, it revealed that this molecule, it has when you look into the structure, it has the geometry of the molecule has a bent double bond, as here it is indicated in this case. When we look into the tin bond, it is called as a bent double bond. So as a result of this bent double bond interaction between the tin atoms, the lone pair on each of the tin atoms, it goes to the empty orbital of the other SN atom. So as a result of which, the interaction, as a result of this interaction, the bond is bent double bond, and it is also called as bent in nature. So other complexes such as COCr.SNCHSCMI32, where tin takes up a trigonal planar environment. Now when we look into figure 4.25, particularly in this complex, here the tin itself, it is present in a trigonal planar moment environment. The SN-C bond here length is, as well as the CSNC, they are less than that of obtained in the derivatives. So these are some of the typical bivalent organometallic compounds of tin. So these are the two. This is figure in figure 4.24. The bent tin double bond is an important and a very interesting organometallic compound, bivalent organometallic compound of tin. So now coming to fluxional organic compound. So when we talk of the word here fluxional, it indicates an interchange. So when we look into figure 4.26, the crystal structure of the molecule, it shows both the two monohapto and two pentahapto cyclopentadienyl rings when we look into this molecule. So here, for example, in figure 4.26, if we look into the left side of the figure and then we compare it with the right side of the figure, we do see an interchange of this FeCO4 group. Initially, in the left hand side, it was present here, whereas when we look into the right hand side of the figure, it is present here. So in from the figure 4.26, we see a migration of the groups, FeCO4 groups. This migration of a particular atoms or groups, it is called as fluxionality. So this fluxional process, this whole process is called as a fluxional process, and this has also been observed from proton NMR, and this is actually this fluxionality, mostly it involves acyclic unsaturated hydrocarbon, and this is a very common phenomena in allyls and allenes. So and here the is that the explanation for this is that for the observed fluxionality in this case in figure 4.26, it could be attributed that to the migration of iron over the allene pi system. So here this is the allene pi system, and the FeCO4, that is the iron group, it migrates over this allene pi system. So this process of migration of iron, it is in this case, or any central metal atom attached with a ligand, is called as fluxionality. So now coming to organocopper compounds and its applications. So organocopper compounds, they indicate that here one copper atom is bonded to the carbon. So organocopper complexes are those organometallic compounds where the M to C bond, that is metal to carbon bond, is copper to carbon bond. That is the metal taken here is copper. So Gilman in 1936, he was the first to point out the he first indicated the presence of organocopper compounds, and currently organocuprates, that is the organocopper compounds are called as organocuprates, and they are currently widely employed for various synthetic organic chemistry. So here we know when we look into the oxidation state of copper, so various oxidation states here, it exists in the following oxidation states like Cu0, 1, 2, 3 and 4. However, Cu0 and Cu4, they are very rare in nature. So the most common copper oxidation state that we currently encounter and we mostly talk is the Cu+2 state, and sometimes in Cu1, and Cu plus 1. However, in coordination chemistry, and that is in organocuprates, Cu plus 1 is the most common oxidation state. Now, when we look into the stability of organocopper compounds, the R that is present in the organocuprates, they acts as nucleophiles and attacks the various organic electrophiles. So the stability could be attributed in the order of this alkyl less than aryl, which is approximately equal to alkenyl, and further they are less than alkynyl. So thermal stability of organocopper compounds, they are increased by substitution of hydrogen atoms by fluorine in the organic moiety, or by addition of other ligands such as phosphines or amines, or by the use of substituents having heteroatoms which provide additional intermolecular coordination sites to the metal, and thus by providing those additional intermolecular coordination sites, they increase the stability of the organocopper compounds. Now, though the mostly the complexes, they are found to possess either linear or T-shaped geometries. However, other geometries are also possible. So now looking at lithium dimethyl cuprate, this is a very common cuprate or compound of copper, and it is a very useful organocopper reagent. It is prepared by the equation that is shown in 4.52. It is first copper iodide, cuprous iodide to be particular, it is mixed with methyl lithium and it forms the lithium dimethyl cuprate. Now, some of the peculiar characteristics of this is that, so compared to the carbonyl group, it can take part in numerous novel reactions because it has a strong nucleophilicity. It doesn't react with any cyano group or ester group, even if it is present in an acid chloride solution. Any halogen atom, they may be replaced with a methyl group by this reagent. So, or this particular lithium dimethyl cuprate, it is an important reagent in organic synthesis because it is widely used in various types of synthesis of new molecules in organic chemistry. Now, coming to here, halogen substitution. So, by interaction with organic halides, it forms C-C bond and they prefer ether or similar solvent. So, if we look at this lithium CuR2, this is a organocopper compound and it reacts with R-X. So, here a compound here it is formed, a C-C bond is formed, and mostly the reaction it takes place in either ether or any other similar type of solvent. So copper is the only metal we know in alkene complexes. Suppose we consider the alkene complexes of copper, we know copper is the only metal which is involved in biological systems, because we know that in many metalloenzymes copper acts as the cofactor. So for various cofactor, and sometimes as the mostly as cofactor, and sometimes we do find it is present in the prosthetic groups. So here in the biological systems, copper is mostly present as a Cu1 complex. So it acts as a hormone in plants and it has also been isolated in this form from plants. So here the reaction is given as for the formation of this type of organocopper alkene complexes. So other alkene complexes, they have been made by direct interaction of CuCl with this, where or with olefins by the reduction of copper plus 2 sulfates salts by trialkyl phosphides. So even copper has been known to form chelating alkenes by it has known to form organocopper complexes by the use of chelating alkenes like norbornadine or cyclic polyenes. So copper, it is quite, because of the presence of this copper 1 complex, we do find copper is one of the, it is the only metal which is involved in biological systems. Now, copper 1 chloride in concentrated HCl, it absorbs acetylene to give a colorless species CuCl2H2 and CuCl2C2H2 minus. So, these halide solutions, they or catalyze the conversion of acetylene into vinyl acetylene or to vinyl chloride, and the reaction of acetylene with hydrogen cyanide to acetonitrile is also catalyzed. So, the reaction of copper chloride in HCl for formation of this has been known for for catalysis reactions. So copper 1 solutions, they copper 1 amine solutions react with acetylenes containing the C triple bond C group to give yellow or red precipitates, which are believed to have this unit that bonded to other copper atom. So the trimer is formed, and it is of this copper acetylene of this type. Trimer is formed when copper 1 chloride is made to react with different acetylene compounds. So the copper acetylides that are formed by the reaction of copper with acetylene compounds, they provide a useful route for the synthesis of other acetylenic compounds and other heterocyclic compounds. Now, a particular important use has been where acetylides are intermediates is the oxidative dimerization of acetylenes. Now, here, although these copper acetylides, they have been used for other purposes, one of the important reaction is they are the intermediates that are formed in the oxidative dimerization of acetylenes. So these are some of the examples of copper organocopper acetic organocopper compounds with acetylene. Now coming to carbonyls. So we know simple carbonyls, they are not stable in nature. So thus this CuClCO, it exists only under pressure. So at a CO pressure of 1 atm, so this the copper organocopper complexes with carbonyl are formed, that is represented in equation 4.58. So here when we look into this, it is also reported that certain amount of CuCO3 plus and CuCO4 plus they are also formed in concentrated H2SO4 under pressure. So when other ligands are present, stable species such as these are also reported. So when we see that organocopper complexes with carbonyls, they are formed under pressure. So also with H2SO4, the complexes, they are also formed under pressure. So at normal conditions, copper does not form a carbonyl complex. Now looking into organocopper complexes with hydrides. So a series of such type of compounds, they have been of lithium copper hydrides, they have been obtained by the interaction of lithium methyl cuprates with lithium aluminum hydride in ether. Like for example, that is represented in equation 4.59. Lithium methyl cuprate plus lithium aluminum hydride, it gives LiAlH2Me2 and LiCuH2. This is the lithium copper hydride, that is one hydride complex, organometallic complex of copper. So with this, we finish the various types of organocopper complexes and their studies. Now we'll start with unit 5, and this unit 5, it deals with metal carbonyls. So metal carbonyls, as the name implies, they contain CO, that is carbon monoxide. So firstly, carbon monoxide, it binds strongly, particularly we know that metal carbonyls, or this is a very carb CO is a very popular ligand for transition metal compounds. So this CO, it actually binds very strongly to these metals because they are not strong Lewis bases. Secondly, most of the time the oxidation state of these metals, it has the CO has oxidation state of 0, and sometimes very low or positive negative oxidation state. But one of the most remarkable feature is that the complexes, that is the carbonyls that are formed, they usually follow the 18 electron rule. So since a lot of them, so they generally follow the 18 electron rule. So many compounds, various compounds, they have been prepared from transition metal carbonyls. Carbon monoxide, it undergoes substitution by various types of ligands, and also the carbon So most of the metal carbonyls, they follow this 18 electron rule. However, there are a couple of compounds that do not follow the 18 electron rule, like VCO6. However, sometimes we do see that MnCO5, it dimerizes to form Mn2CO10, and then it follows the 18 electron rule. But particularly in case of VCO6, it doesn't dimerize because dimerization of VCO6, it will give a dimer, that is V2CO12, where the metal, each metal would have a coordination number of 7, and this is not a stable compound. So that is why the VCO6, it is less stable than carbonyl complexes which obey the 18 electron rule. So because it is less stable, it decomposes at 70 degrees centigrade, and it readily forms an 18 electron species by accepting an electron given as this. So one exception to 18 electron rule has been the VCO6, but it forms a stable species by accepting an electron and forming VCO6 minus. Now coming to the different preparation and properties of metal carbonyls. So nickel carbonyls, they are most, and iron pentacarbonyls, they are mostly used. See the in equation 5.2 and 5.3, we see that the reactions for the formation of nickel tetracarbonyl and iron pentacarbonyl, here the temperature for nickel, the temperature is 25 degrees centigrade, and for formation of FeCO5, the temperature is around 200 degrees centigrade. So these are two of the easiest carbonyls to that can be obtained. Now this nickel tetracarbonyl, it is very toxic in nature, and it is a volatile colorless liquid. So it's dense, it is with about 6 times dense as air. Now when the iron pentacarbonyl, it is yellow red in color, and it slowly decomposes in air. FeCO5 on photolysis, it gives the orange solid Fe2CO9, that is represented here in equation 5.4. Then another method of preparation of carbonyls is called as the reductive carbonylation. This is also a very commonly used method by which other simple metal carbonyls can be obtained. So in this process, carbon monoxide and a reducing agent, sometimes carbon monoxide is also used as a reducing agent, they act on a metal oxide. Or particularly most of the cases metal oxide is used, or sometimes metal chloride might be used, and then the respective carbonyls are obtained. Like majority of the carbonyl complex, they are formed when the metal is reduced in the presence of carbon monoxide. Like if you look into the equations 5.5 to 5.9, we see here chromium chloride plus Al plus 6CO, it gets reduced to form CrCO6. And other equations, such equations has been represented here, that indicates reductive carbonylation for the formation of metal carbonyls. Now other methods of preparations, they are also here represented in equation 5.10 and 5.11. This in 5.10 we can see the preparation of VCO6 using diglyme, and in equation 5.11 we can see the preparation of W, that is tungsten hexacarbonyl. So these are some of the unconventional methods. Now, and the three methods that we studied, they are used particularly for the synthesis of simple metal carbonyls. Now we want to look into the preparation of polynuclear carbonyls. So like here for example, in that is in equation 5.12, we can see polynuclear carbonyls, they are obtained by thermal or by very complicated decomposition process of carbonylate anions in alkaline media. So in equation 5.2, here we can see, here a salt is present, and here MnCO5Br in THF solution, we can see a polynuclear carbonyl, here it is complex is formed. So these are two equations that show the formation of polynuclear carbonyls. So now coming to 18 electron rule. So 18 electron rule is, it deals with the calculation of the number of electrons that are present in the central metal atom. So if you look into the 18 electron rule, here a large number of metal carbonyls, and we know even halogen substituted metal carbonyls, they all usually they obey the 18 electron rule. So 18 electron rule, it is used to find the total number of electrons around the metal atom, and it has been found that this number usually corresponds to the atomic number of noble gases like that of krypton, xenon, and radon. So when we count the total number of the electrons that is present on the central metal atom, then 18 electron rule, it indicates that this number should be equal to the atomic number of noble gases. So then only we can say that the metals have an effective atomic number of the noble gases, or we say that the metals, they obey the EAN rule. Now EAN is what we call it as the effective atomic number rule. So the total number of electrons is calculated by considering the number. There are actually four rules that we need to follow for the calculation of the effective atomic number. So for this, here counting of electrons in complexes, here it is done, and the five basic steps have been listed below. So first, for the calculation of the EAN, we must know the number of electrons that are present in the valence shell of the metal atom. This is the first step. Then we'll have to look into the charge of the metal in the complexes, and accordingly we have to add or subtract the electron. So the primary step, it deals with the finding the exact number of electrons that is present in the metal valence shell of the metal atom. Secondly, we have to find out the number of the electrons from the ligands that contribute to the valence shell of the metal atom. So like, since we are talking about CO, each CO ligand, it contributes two electrons. So similarly, other ligands, their contributions have also been listed. So depending on a number of the ligands that are attached to the central metal atom, finally the number of electrons is calculated. Next, if any conventional ligands are present, then the number of electrons contributed to the valence shell is also again calculated. Now if in the complex there is a MM bond, then one electron is added for each metal. So then we can find out how many electrons are donated to the total metal. Then adding all of this, we can find out the effective atomic number of the central metal atom. Now, mostly it has been found that the metals with odd atomic numbers, they cannot satisfy the EAN rule by simple addition of the CO ligands. So there are several options open to these metals by which 18 electron rule can be satisfied. So the simplest is the addition of one electron by reducing agent to form the carbonylate anion. This is particularly useful for metal atoms which have odd atomic number. So now there are other stable compounds which other than 18. So it is always not that the stability of a compound is indicated by 18. So in certain compounds, we need to calculate the CFSE and other factors. There are certain metal carbonyl compounds of D blocks that obey 16 electron rule. Even we have just studied that VCO6, it has 17 electron, and therefore it is called as a 17 electron species. Now the VCO6, it accepts another electron to form VCO6 minus, and thereby satisfying the 18 electron rule. So therefore, so it is not always that the stable compounds must be following the 18 electron rule. So we have also certain exceptions to this case. Now here in this, the oxidation, the electron count is an important process. For it is actually very crucial, the number of electron counts for determining the EAN of a particular metal. So here when we have, suppose we have a dimeric species, if we look into the dimeric species like Mn2CO10 or CO2CO8, then these are stable in nature, and then here we have a metal single bond. So that is the contribution of a metal single bond is one electron for each metal. So likewise we have to calculate. So here in particularly in one case, an example has been shown for CO2CON and how an 18 electron rule is followed. So particularly in table 5.5, the contributions of the ligands to electron counting is listed. So here what we see is, for the carbonyl ligand, the electron count is 2. So for thiocarbonyl it is 2, for amine it is 2. Now, and here others are listed like halogen, it is always 1, for alkyl it is 1. So these are some of the common contribution factors that we must be knowing for calculation of a effective atomic number of a particular metal. So depending, so this is a very important, this table is very important. And so the basics, so the minimum of ligands and their contributing factors must be known to calculate the EAN. So here in table 5.2, some common ligands, they are the details of some common ligands found in organometallic compounds, they have been listed. And there are, so here there are several exceptions to 18 electron rule. Sometimes molecules with 16 valence electrons, they are stable in nature, or even stable, they more stable than 18 electron. So there are, we do come across certain molecules which have 16 valence electrons, and they are more stable than the complexes having that follow the 18, that is the EAN rule. So such cases, they are found to be true for the metals, particularly for the bottom right corner of the transition series, that is for the elements particularly rhodium, PD, IR, and PT. So here these particularly iridium and platinum, they have been known and they have formed stable 16 electron molecules. And these compounds, they have been isolated and they have been widely used in synthetic organic chemistry. So here in figure 5.1, we can, some of the stable organometallic compounds that do not follow the 18 electron rules, they have been listed here. These compounds, they are found to have D8 metal atoms, and they are mostly square planar in nature. So these are some of the examples. So now some intermediates in organometallic compounds, they have been confirmed, which is an exception to this rule. There are now the question of stability of 16 electron complexes arises. So why they are stable? The stability of these 16 electron complexes has particularly been attributed to their D8 contribution. D8 configuration, that is the square planar, it is not discriminated against relative to TBP, trigonal bipyramidal. These D8 particularly configuration, they have similar chance and they have a similar relative to the configuration to 18 electron rule. So now this is all about the 16 electron complexes. Now we will talk about NO. NO is nitrosyl and it is an odd electron molecule. So it has possessing not only a nitrogen donor lone pair but also one electron in the pi star molecular orbital. So by convention, we treat NO as coordinated NO plus with the extra electron counted among the metal or other ligands. So in other conventions, NO has been treated as a 3 electron donor as NO minus. However, in simpler terms, we have always considered NO analogy NO plus as analogous to CO, Cn minus and N2. So the NO plus ligand in the complex, it involves it pi star MOs with the metal d pi to a considerable extent, and some net electron density is also distributed between the metals. So the electron counting in NO complexes, here it is illustrated by the following example. Suppose we see MnCO4NO. So the for particularly here NO, we represent it as NO plus. Here one sigma pair. So here it is one pair that indicates two electrons. Then for CO, here it is one sigma pairs, and here Mn minus 4 pairs. So overall it is 9 sigma pairs. So 9 sigma pairs, it indicates 18 electrons. So this is how the 18 electron counting is done in complexes, that for nitrosyl complexes. So now we are coming to the again the electron counting in cyclopentadienyl structure. So this ligand is very important in organometallic chemistry, and here this particularly the pentaheptocyclodienyl, that is here it is presented in figure 5.3, it is widely used, and here the structure here is represented like this for the pentaheptocyclodienyl ligand. And the particularly the calculation of electrons for this complex has been shown as, if we look into this complex, we have 2 CO, so therefore it contributes to 2 sigma pairs. For the eta 5 position and C5H5 minus, there is 3 sigma pairs. For the eta 5 C5H minus, here there is 1, and we have corresponding to Fe. So here the Fe is present as Fe2 plus and 3 pairs. So total is 9 pairs or 18 electrons. So here the simple that this is how we calculate the number of electrons in various complexes. So some of the examples they have been listed here. Now here the structure of the example of a diene metal complex here it is given, and the hydrocarbon here in figure 5.8, this is a cycloheptatriene represented. So based on looking into the various structures we will find the calculation of electrons is done. So now we will look into a complex that is a diene metal complex. Here it is given as FeCO3 eta4C4H4. Now this C7H8 is cycloheptatriene and it is represented this. It is an isomer of norbornadiene and it has a flexibility in the number of donor pairs it can provide. So it acts as a neutral 3-pair donor as shown in figure 5.9a. So this acts as neutral. However, to pair and the or it appears as a diene, and that is why it is a metal, very commonly used metal diene complex. Now in this section for the properties and structure, we'll study some of the common properties of binary carbonyls. So most carbonyls that we come across like FeCO5, OSCO5, nickel tetracarbonyl, they are all liquids at ordinary temperature. So some of their, however, other other carbonyls like CO2, CO8, they react at ordinary temperature. FeCO5 and nickel tetracarbonyl are also easily oxidized. And here in table 5.3, some of the common properties of stable binary carbonyls here they are listed. Now all metal carbonyls, they are solid, and only the exception are the mononuclear carbonyls of iron and nickel tetracarbonyl. So all mononuclear carbonyls, they are not having any color, but polynuclear carbonyls, they are associated with some color. Now nickel tetracarbonyl, it has a tetrahedral shape as it is shown in figure 5.10. It has linear NiCO bonds and the bond length has been here, it has been represented. If we talk about FeCO5, that is pentacarbonyl iron, it has TBP structure. Here it is shown in figure 5.10b. And the difference, and this particular structure has been confirmed by X-ray diffraction. CrCO6 has octahedral structure, and this is also, the figure is not given, but it has octahedral structure. Then coming to binuclear carbonyls, particularly in binuclear carbonyls, we have the presence of a metal-metal bond. The CO ligand, it can fulfill different structural properties and it has 3 different bonding modes. So here the details of the new stretching frequency for various binuclear carbonyls, it has been reported here. Now if we look into Mn2CO10, it has a structure composed of staggered MnCO5 units which are joined together by a Mn bond as shown in figure 5.11. So here in this figure, this structure is shown in its simplified form. Here this is the staggered form of the Mn2CO10, and here in this right side the structure has been expanded for simplicity. Now FeCO29, if we look here in FeCO29, it has both bridging and terminal groups. This molecule, it is diamagnetic, and here each Fe molecule is linked to 3 bridging CO groups. So the bridging bonds are longer than the terminal bonds, and particularly in this case, the coordination number of Fe is 7. And here the figure is shown in the structure of Fe2CO9. Here it is shown in figure 5.12. Then coming to CO2CO8, the structure here it is shown in figure 1.13. It exists in 2 isomeric forms. So one has a bridging structure and other has a non-bridging structure. The bridging structure here it is shown in 5.13a, and the non-bridging structure here it is shown in figure 5.13b, and both these structures they have been confirmed from X-ray diffraction and X-ray crystallography, and they have been listed here. So here now again coming to bonding in carbonyl compounds. So the nature of bonding between the carbon monoxide ligand and the transition metal is the main is very crucial for indicating the stability of the carbonyl compound. So we know here in figure 5.14, the molecular energy level diagram of CO has been represented. So here on the left hand side, the atomic orbital configuration of C has been shown, and here in this right hand side, the for O atom has been shown, and in the middle part it represents the MO of the CO molecule. So this is done for the carbon monoxide molecule. We know that the HOMO is sigma 2p orbital, which is derived from the high energy 2p carbon and oxygen species. So the lowest unoccupied, that is the LUMO, are the pi star 2p antibonding orbitals. So when we look into the MON diagram, we see that the all bonding orbitals, they are occupied fully, and they result in triple bond of carbon monoxide molecule. So there is also one lone pair available here, the in the carbon atom, which may be donated to the metal center through bonding. So this is how the MO of CO looks like. So again, predominantly, so because the contribution comes from the 2p atomic orbitals of carbons, so what happens is the carbon, the rather approximate shapes are decided on this. So here, according to the representation here in the figure 1.4, the various assumptions are made, and what happens here is this, particularly the molecular energy diagram of CO, it leads to a very important concept which we call it as the back bonding. So what happens here is there is an, particularly we see the overlap of the end of the sigma HOMO of the carbon monoxide with an empty d orbital of the metal, that is mostly monoxide. It acts as a Lewis base, and it donates a pair to the metal that acts as a Lewis acid. Now this donation of electron density through carbon, it occurs, of this donation occurs. So because of this donation, there is a very high increase in electron density on the metal. So as a result of this increase in electron density on the metal, to delocalize this electron density, there is a simultaneous bonding which we call it as the back bonding or synergic bonding. Now this back bonding, it is achieved by an overlap of the filled d orbital on the metal with the pi star LUMO of the CO. So these two orbitals, they have the correct symmetry to allow for this interaction, and thus the electron density is removed from the center back onto the CO to some extent. So as a result, this results in the charge transfer. So and this is a d pi p pi bond. So thus, because of this back bonding, a double covalent bond between the metal and carbon atoms, they exist. So according to this representation, the electrons, they would be pushed into the pi antibonding of the carbon monoxide. So what happens, experimental results have shown that carbon oxygen bonds in carbonyl compounds, they are longer and they are weaker that in comparison to pure carbon monoxide in nature. So other ligands, they can bond to transition metals through this concept of back bonding, like alkenes and phosphines, but they are not as good pi acceptors as carbon monoxide. So back bonding clearly explains the stability of carbonyls, metal carbonyls. However, with the concept of back bonding, other complexes using alkenes and phosphines, these ligands, they can also be attached to the metal carbon center. So the metal atoms here in metal carbonyls, they have low oxidation states, which may be negative, zero, or low positive. So well, this, if we look into, suppose we consider the sp3 hybrid orbital in nickel tetracarbonyl, the dsp3 hybrid orbital of FeCO5, then we see this type of bonding, the synergic bonding or the back bonding, that has been represented here. It represents the back bonding in NiCO4 and other such metals. So this, with this back bonding, the metal carbonyls, they explore and they are endowed with certain stability. So now some of the important reaction of metal carbonyls. Suppose if in equation 5.15 and 5.16, the when FeCO5 is heated with alkali, then oxidation occurs, followed by oxidation with MnO2. These products are formed. So the most important reaction is formation of carbonylate anion by addition or addition of alkali or reduction here is shown. So formation of carbonyl hydrides also takes place. So here formation of carbonyl halides, and these are some of the important reactions. Displacement of CO, the formation of nitrosyl also takes place. So these are certain some of the reactions, important reactions of the carbonyls compound. Now coming to the vibrational spectra of metal carbonyls. So vibrational spectra, as we know, it particularly uses the IR stretching frequency data, that is the infrared spectroscopy. So here, and this IR, if we look into the, since it deals with the stretching mode, these are the two stretching modes that has been represented in a carbonyl. One is the asymmetric stretching and another is the asymmetric stretching. So here, since they have a resultant dipole moment, so these molecules, they are IR active in nature, and the bands that are expected, they are mostly due in IR spectra, are mostly due to these symmetric stretching and asymmetric stretching. So a mononuclear carbon, in, suppose we perform the IR spectra of these carbonyl compounds, the location of the peak position, it indicates the type of the stretching that is occurring inside the molecule. So infrared spectroscopy, it is a powerful tool for investigating the structures of carbonyl compounds. So from IR spectroscopy, we can know the CO bond order and also the frequency. Thus, the frequencies of absorption that is particularly used for CO metal, it can be indicated by this. The free CO, it absorbs at greater frequency than metal carbonyl cation, the neutral metal carbonyl, and followed by a metal carbonyl anion. The stretching frequency in general of CO bond, it vibrates around 2143 centimeter in gaseous state. So here the vibration frequency, if we look into the different back bonding in IR spectroscopy and vibration spectroscopy, if we consider, then by looking into the figure here in table 5.6, various infrared CO stretching frequency of mononuclear carbonyl complexes has been given. So by looking at the IR spectrum and assigning the correct frequency, we can find out the actual nature of the frequency of the carbonyl complexes. So here in figure 5.17, we see the IR spectra of carbonyl region of FeCO5 that are associated with different stretching vibrations. So here in this is a IR spectra. The x-axis, it represents the wave number, and in y-axis it represents the percentage transmittance. So and then here, for particularly in this spectrum, we come across two peak positions, one corresponding to 1900 and the other at 2200. So here in this, we two different CO stretching frequency and their intensity are also different. So we find out, so this is how we interpret the FTIR data, and by looking at their IR active modes and the observed frequency, we can assign their point group and their geometry. So now if we look at the IR stretching frequency of the following complexes, in all these complexes, the only difference lies in their R group. So here for this complex, the IR stretching frequency, the CO stretching frequency is observed at here and here and here. So of all these complexes, the methyl groups on here PME3, it shows a plus I effect. So but here in PF3, it has the electron withdrawing fluorine group. So that is why we see here an increase in the absorption. So now, so with this data, we can say that the nature of the groups, the ligands, it plays an important role. It also has an important role in deciding the stretching frequencies that is observed in the IR spectra. So here in table 5.7, the IR stretching frequencies of neutral and anionic carbonic complexes have been listed. So some of the in table 5.8, 5.9. So other stretching frequencies, the bond lengths. In table 5.9, the CO bond lengths for polynuclear carbonyl complexes has been shown. The stretching frequencies of different carbonyls, here it has been shown. So in conclusion, we can say that when we actually obtain the IR of a metal carbonyl, it is actually taken in a vapor phase. So here, rather than the solid phase method, we always prefer the vapor phase. That is, here This in figure 5.18, we show the IR spectra of Fe2CO9. So it has strong regions. We can find out it has very three strong peaks in this region, and it indicates the presence of both terminal and bridging CO. And this was further confirmed from different X-ray studies. So here in figure 5.19, the FTIR spectrum of Fe2, CP2, CO4 is given. So when we look into the spectra, we do find three peaks which correspond to both bridging and terminal CO, and thus particularly the here we know that the bridging CO ligands, they absorb in the lower frequency. So here, since we see that the two bridging CO groups are almost in the same line, so here, and that is why they have a low symmetry, and so thus these two, they should be for the bridging CO. So this is how, looking at the FTIR spectra, we decide on the structure of a particular complex. Now here some of the examples that have been shown how to calculate how to predict the structure of different complexes from the IR data. Now coming to CO stretching frequencies and their force constant. So first we'll try to find out the relation of the CO stretching frequency with bond order, and then we will determine the electronic structure of such metal complexes. So first, as the electronegativity of R it increases for different type of molecules, the CO stretching also increases. So now with the increase in the R type of, then the CO also increase. Then we should look into which type of atom, whether the CO is attached to it, the type of the complex is formed. Here we will look into it, and further then we will find out the IR spectra, and then we will decipher the structure. So this is how the various assignment of structures and here they have been given. So this is all about your IR spectroscopy, the various structures that have been elucidated for. However, one problem with IR spectroscopy is that it is very difficult to elucidate the structure of a polynuclear carbonyl. So although IR has been very useful for simple carbonyls, for polynuclear carbonyl it is very difficult. Now even bridging carbonyl compounds can often be detected, but in complicated structures the spectral interpretation is very difficult. So, and in today's world, rather than using infrared spectroscopy, most of the studies and confirmation about their structure has come from X-ray crystallography. So now we'll start with metal pi complexes. We'll just take a break of 10 minutes and again resume with metal pi complexes. So now I'll be starting with metal pi complexes. The unit 6 it deals with the first part of the metal pi complexes. So here, so before going into metal pi complexes, we will view the classification of organometallic compounds into three different classes. So although we have studied this, the classification of organometallic compounds, but based on the type of the bonding present between the metal and carbon atoms, classification has been done, and they have been classified into three categories. The first one is the simple metal organometallic compounds like the metal alkyls and metal aryls, where the metal carbon is the conventional electron pair sigma bond. In the second class, that involves the MC bonds, where the ligand molecule is serves both as a sigma donor and a pi acceptor, like CO and PR3. They are compounds of this type. In the third type of organometallic compounds, the ligand they serve as a pi acceptor, as does the CO in some compounds. Here the electrons that are donated by the ligands, they are not sigma non-bonding electrons, but they are pi bonding electrons. So bonds of this type, they are not isolated, like they are not only isolated double bonds in olefins, but they are also obtained or observed in extended pi systems. So a single organic ligand, it can donate like 2, 3, 4, 5 or 6 electrons from the pi systems to the metal, that depends upon the size of the metal. So then depending on the number of the pi electrons donors, so 1, 2, 3, 4, 5 and 6, and many such metal pi complexes have resulted. Now coming to transition metal nitrosyl complexes, so here in these complexes, NO, that is nitrogen monoxide, or nitric oxide, it contains these, is present in such metal transition metal complexes. So when we look into the valence electronic configuration of NO, we know that there are total 11 valence electrons, and the molecular electronic configuration, molecular orbital electronic configuration is given as here in figure 6.1. We see the molecular level diagram for NO. Now here we see a single electron, here it is present in the sigma, in the pi star 2p orbital. So because of this, we know that NO is paramagnetic in nature, and thus because of this presence of single unpaired electron, it behaves similar to those of alkali metals. Now here also we know that NO, it gets readily oxidized to the NO plus cation, and this NO plus cation is isoelectronic with N2, that is dinitrogen molecule, and it has a bond order of 3. Since we know that it has a bond order of N2 has a bond order of 3. So if the NO radical, it is bound to a metal, then it is called as the nitrosyl ligand. So this behavior, if the electron pair, it occupies the low lying metal based molecular orbital, then the nitrogen here, it functions as a both sp sigma donor with back pi back bonding, and this is what similar to that of the carbonyl ligands. But here if the metal is an electrolyte system, then the pair of electrons, it has to reside on the non-bonding orbital of the nitrogen, while the low-lying orbitals on the metals are filled. So this results in a trigonal hybridization system. So now free NO, it exists as both as a stable radical, free radical, due to the ON-NO bond in the dimeric state. So we can construct NO from CO by adding an extra proton, like to the carbon nucleus, which is analogous to like CNO plus. So if you look at this model, then in bringing CpMoCO2, and together we have to first remove the unpaired electron. Now, so to elaborate this, NO as a ligand, it can coordinate in different metal complexes. So like it has linear sp hybridization, in bend shape sp2 hybridization, and in bridging pattern, it is sp2 hybridization. So these are the different modes by which nitrosyl ligands can be coordinated with the central metal atom. Now the conversion of a linear to a bent NO is considered to increase in the formal oxidation state by 2 units. So raising the electron density on a metal, it will encourage the linear to bent conversion, because in the bent NO, a pair of electrons that originally was becomes a lone pair on the nitrogen. So thus here we can see the electronic structure in figure 6.3, the electronic structure of NO and its binding to a metal by both covalent and ionic models. So here in figure 6.13 complex, these are two very peculiar examples of complexes that contains bent NO bonds, and the structure has also been confirmed from the IR stretching frequencies given to this, which indicated their bent structure. Now a derivative of Vasquez complex, that is here it is given in equation 1, it is the first characterized bent nitrosyl ligand. This complex was the first to be known for the bent nitrosyl ligand. The geometry here it is shown in figure in equation for this. In equation 1 it is the for this complex it is a square pyramidal with the bent nitrosyl ligand having a bond angle of 124 degree, and here the for this complex here it is shown in figure 6.4a, and the and another group that is for the bent nitrosyl ligand has been shown in figure 6.4b. Now when we take a ligand and we try to consider the number of n is the number of ligands that are attached to the metal M, then particularly a 17 electron fragment can bond to NO to give a bent 18 electron nitrosyl complex. So here the discovery that NO and CO they are important molecules in the mammalian brain. They have been known to get typically nitrosyls with some and their preparation methods. It has been shown here in these equations. When we look into the equations from 6.5 to 6.9, so these are the preparation methods. The first two cases they show linear bend equilibria. That here equation 5 it shows that NO unlike most ligands it can replace all the COs in a metal carbonyl. The last two equations it shows the use of the stable NO plus which is isoelectronic with CO that is used in the synthesis. Now NO plus it is a powerful oxidizing agent and it is capable of oxidizing many bulky metals as shown in equation 7, but the resulting higher oxidation states it cannot usually bind to NO. So there are hardly any complexes with nitrosyl ligands alone, like we have complexes containing only carbonyl ligands, but we don't have complexes that are just containing the nitrosyl ligands. So but a large number of mixed carbonyl nitrosyl compounds are known and they are formed by the reactions shown in equation 11 and equation 12. Even though CO and NO they have comparable properties, CO may be utilized in excess and high temperature and pressure, whereas nitric oxide, the use of NO in excess, it leads to unwanted oxidation process. So nitric oxide that is NO is usually replaced with nitrosyl chloride, nitrates and other reagents like those represented here in equation 16 to equation 15. Now in equation 6.16 it shows how a dimer can be formed from the parent nitrosyl compound. Using this equation 6.16 it depicts the formation of a dimer from a parent NO compound with the use of NaBH4. Now transition metal dinitrogen and dioxygen complexes. So first we'll start with transition metal dinitrogen complexes, that is N2 molecular nitrogen. This N2 it is a isoelectronic with both CO and NO. So although there are a number of complexes of CO and NO plus, even dinitrogen complexes N2 was difficult to obtain because it is a weaker sigma donor as well as a weaker pi acceptor than CO. It has a very less binding affinity. So only good pi donor metal atoms they bind strongly with N2. So here in equation 17, 6.17, the reduction of the ruthenium compound, and equation 6.18 is shown the formation of the dinitrogen complex. So first the reduction of the ruthenium compound occurs and further the formation of the dinitrogen complex here is shown. So in figure 6.5, the first example of the transition metal dinitrogen complexes obtained from ruthenium RuNH3 whole 5 N2 plus. Here it is shown. Dinitrogen, it is a strong nucleophile which is shown by its displacement of water as shown in equation 6.9. Since it replaces water, thus it is a strong nucleophile. So the metals that can be bridged to dinitrogen molecule, they has been shown in this way, figure 6.16. This is metal bridging by the dinitrogen molecule, and this is how nitrogen remains in the bridging structure. However, if back bonding occurs in these complexes, then the bridging structure, it changes to this form. So this occurs because of the back bonding occurring from the metal atoms. Now majority of the complexes, they have terminal eta 1 and 2 link where bonding is similar to that of a isoelectronic co-ligand. Now sometimes dinitrogen ligands, they bind in a side-on type of mode. Here it is a side-on type of mode binding for the N2 ligand, which is shown here. Now the IR stretching band for particularly for the dinitrogen ligand, it lies in the range of 2150 to 1900 centimeter inverse, and this is the particular range observed for the IR stretching frequency. Now most of the transition metals that have been used to prepare N2 complexes, they have been, the research is currently going on, and they have been synthesized with a large number of transition metals here as it is shown in figure 6.1. Here the unshaded regions, they are the, it represent the elements which form mononuclear dinitrogen complexes. However, the where they are shaded, so that indicates higher complexes. So when we look into figure 6.9a, here a complex is shown with cobalt, which is the first example of a transition metal dinitrogen complex that is prepared directly from gaseous N2. In figures, this complex CO N2 whole 3, this complex was directly prepared using gaseous N2. So here in figure 6.9b, this is the first example of the molybdenum dinitrogen complexes. So these are two crucial examples. In a nitrogen metal complex, other ligands like phosphine halides and water can coexist. The nitrogen fixing bacteria, that is nitrogenase, it converts nitrogen to ammonium ions catalytically. So what happens here is, in these bacteria, the active sites, it contains Fe, iron, molybdenum and sulfur. So these, they coexist together and they help in the nitrogen fixation bacteria, that is the nitrogenase. Now the method of preparation of N2 complexes with different metals. So first is by using nitrogen gas directly. So the here in, if we look into this equation 6.20, direct N2 gas has been used, and however this is the actually the process of fixation of nitrogen by the bacteria nitrogenase. However, the mechanism for this reaction is not yet clear, but nitrogen gas has been employed for the preparation of these compounds, nitrogen complexes. Now here pi Cp2 TiN2 TiCp2, this complex is fully methylated derivative and it has been synthesized in ether. Here if the titanosine is exposed in benzene for a long time, then pi Cp2 TiN2 it is formed, and similar titanosine, that is the titanosine dimer plus N2, it forms titanosine dimer N2, it has also been obtained. So isopropyl magnesium chloride, it reacts directly with N2 to form a complex, and here it is represented here. The Grignard reagents, they have also been used to prepare N2 complexes of molybdenum. So these are certain examples that involve directly the use of nitrogen gas in the preparation of various types of complexes. Then the preparation of compounds containing chain of nitrogen atoms. Oxidation of coordinated hydrogen, it first produced the dinitrogen complex of manganese, here H2 from H2O2 in presence of Cu2 plus and THF, then dinitrogen complexes has been formed. Osmium tetrahydride has been formed there. These are some of the reactions for the preparation other than N2 gas. The preparations has also been made in which nitrogen atoms, they are combined to give a nitrogen complex. Here in equation 6.30, it is successful only for osmium, however, and it has not been found for other metals like molybdenum and ruthenium. Then transition metal dioxygen complexes. So here in this transition metal dioxygen complexes, O2 is used. The antibonding molecular orbitals, of O2, they are half filled. So here they can take up two electrons, and as in this process they have different forms are obtained, like superoxide ion O2 minus, O2 minus, peroxide ions O2 minus, and different. Here that the bond order and internuclear distances of O distances have been reported. It is found that all the different charge forms of the dioxygen molecule, they will, because of the different nature of their charge, so they will different bind to different ways with different transition metal ions. Now here in figure 6.10, two models of binding dioxygen molecule has been shown. That has been the, in figure A it represents a end on binding mode, whereas in figure B it represents a side binding mode. Now, myoglobin and hemoglobin, these are two important molecules in our body. They are both used in the transport of blood across our body, and that also involve the transfer of an electron from the metal to O2, resulting in the formation of a superoxide ion. So here, this in figure 6.11, the side-on binding of O2 in metal complexes has been shown. There are maybe many metal complexes that contains two metal ions in a complex, and here particularly in complexes that contain two metal ions, the dioxygen molecule here it is bonded in three ways. And here it is shown in 6.12 ABC in different modes. Here the different modes have been represented when two metal atoms, they are present in one complex and they are bonded to dioxygen. And here some of the examples of such complexes have been given. Now most of the transition metal ions, they have oxidation states mostly ranging from 2 to 6. They bind with dioxygen. So in these complexes the metals they have that have higher oxidation state than their usual ones. So these metal complexes, they are diamagnetic in nature, but sometimes paramagnetic has also been reported. So the oxygen metal complexes, they contains various types of like hard and soft ligands, and therefore the coordination might vary. So a few important dioxygen metal complexes are hemoglobin and myoglobin. These are the two proteins that bind, and they are used in the transport of oxygen or blood in our body. The hemoglobin that is found in RBCs, where myoglobin it is a cell protein. So they have a mostly the base structure consists of a porphyrin ring with the iron 2 plus ion. It is present at the center of the porphyrin rings, and that porphyrin rings they bind to oxygen here as it is shown in figure 6.14a, the structure of hemoglobin and oxyhemoglobin. So oxyhemoglobin is formed after the binding of the oxygen dioxygen with the hemoglobin and forming this type of complex. Now another important dioxygen complex has been the Vasquez complex, which is actually transchlorocarbonyl triphenyl phosphine iridium complex. It is square planar in nature, and it is diamagnetic in nature. So when oxygen binds to this complex, Vasquez complex, it undergoes the oxidation state of iridium changes from 1 to +3, and it occurs via a oxidative addition, as here it is shown in equation 6.32. Now hemocyanin is also oxygen transporting molecule found. So deoxyhemoglobin is the colorless compound when oxygen is removed from it. A blue colored complex results when the two units bind with the dioxygen molecule. So this dioxygen molecule, it binds to the copper and forms this type of complexes. So the best method to synthesize dioxygen metal complexes is to directly expose the metal ion solution to the gaseous O2. So to achieve this, we can bubble the oxygen, the gaseous oxygen, into the metal ion solution. So this is known as oxygen activation, and the process is known as synthetic oxygen carriers. So in this mechanism, in this process, the oxygen, the dioxygen, it attaches to the metal in the reversible manner. So if irreversible oxygen binding occurs, then the metal ions, they are to higher oxidation state, and thereby the compounds are suitable for homogeneous catalysis. Here in the reaction was done by treating precursor rhodium 1 complex with oxygen at 3 atm pressure. A dark color product in C6D6 it was observed, and from the red color, and it formed this red color product as shown in equation 6.34. So other peroxo dicopper complexes have been here particularly a peroxo dicopper complex has been prepared, and it is represented in equation 6.35. So other routes for the synthesis of dioxygen metal complexes have been listed here in equation 6.36 and 6.37. So now coming to tertiary phosphine as a ligand. So now tertiary phosphine, this is the, as per the definition, like phosphine complexes, they do not have any direct metal to carbon atom, and so thus they are not organometallic in nature. Since phosphine, it involves ppH3, they do not have any metal to carbon atom bond. So technically speaking, they are not organometallic in nature, but because they have lots of similarities with that of carbon monoxide, so that is why substituted phosphines like PR3, PR2AR, these molecules are used, and these the tertiary phosphines, they are one of the those ligands where electronic and steric properties may be changed as by varying the value of R. So here figure 6.15, it represents the loosely referred to as this figure, it represents DPPE, and they are loosely referred to as phosphines. Now phosphines, the in figure 6.16, here the sigma bond from ligand to D metal and pi bond from metal to ligand in phosphine, here it is noted. One of the important thing to note here is that here no back donation occurs. So the sigma star, it is not susceptible to back donation, like we observed it in the case of sometimes in nitrosyls and in particularly carbonyls. Back bonding here, it is not possible. So when we look into the molecular modeling software, here a cone type structure, the determination of it here, the cone type structure for this, they have been, has been metal phosphorus bond, it has been observed. So in figure 6.17, it shows the cone where the angle is found. So a useful result here to obtain this, it is called as the cone angle theta. So and this determination has been done. So these are called as actually Tolman cone angles here in figure 6.3. The various types of phosphines and their cone angles in degree, it has been reported here. You can see it is for PF3, PCl3. So various types of phosphines with their cone angles, they have been reported. So regarding their pi donor and pi acceptor properties, it is found that as the average electronegativity of the three groups attached to P increases, the ligand, it becomes a poorer sigma donor but a better pi acceptor. So thus the sigma donating ability of phosphine is actually inversely proportional to its pi acceptor ability. So in summary, we can say that the electron rich phosphines like PME3, they are good sigma donors and poor pi acceptors, whereas the electron poor phosphines like PF3, they are poor sigma donors and good pi acceptors. Now polyphosphines, they show that the sigma donor pi acceptor properties of each phosphorus atom, they follow the same trends, but the structure of a molecule is decided by considering the different additional steric configurations. So before going to polyphosphines, we'll first consider with monophosphines. The triphenyl phosphine and trimethyl phosphine, these are the most common monophosphine that is available. So others are also available. Many of them have longer R chains. So some of the examples of mixed phosphines here, they have been listed here in figure 6.18. Sulfolated triphenyl phosphines are examples of phosphine ligands. They for water complexes, and here they have been phosphoadamantane in TPA here has been shown. So aryl phosphines have also been formed and they have substituted arenes while bonding to metal atoms. Here in figure 6.20, the bonding of aryl phosphines with metal atoms has been shown. Now in equation 6.38, an application is shown where an intermediate forms, and the design, this follows the design for a molybdenum tungsten compound, it happens. So this is how the design for starting with a phosphine, it goes towards the formation of a molybdenum tungsten compound. It is shown in figure 6.38. Then after monophosphine, we have diphosphine ligands. The chelated or bridge complexes, they are formed from these ligands. The examples include this bis DMPE, that is DMPE, it includes, it indicates dimethyl phosphinoethane. DPPE, it indicates diphenyl phosphinoethane and such. And here in figure 6.21, the various structures they have been indicated. Now ligands, here in 6.23, the chelating capability of the diphosphine ligands have been here, they have been indicated. So this is how they serve as in capable of chelation. Chiral complexes, they can serve as catalyst, and then it is required to provide chirality on complexes. So chiral diphosphinoethanes, they have been used, and they are also such type of chiral phosphines, they have been used for particular purposes. The diphosphines with long chains between the p atoms, they may occur the transposition, as here it is shown in that their large ring diphosphines are possible. They may either occupy the they mostly occupy the transposition. Here the trans isomer is more stable than the cis isomer, where the octahedral complexes are present. So such type of cases are also cyclic diphosphines are also possible. So more biphosphines which are quite important, they are the asymmetric binaphthides. Here it is shown in figure 6.27a, and here in figure 6.27b, it is 1 dash diphosphonoferrocins. These are, they mostly serve as chelating or bridging ligands. Then after this chelating phosphines, we have the polydentate phosphines, the tripods such as CH2, PR2 whole 3, these are of importance here. So these ligands of the tetradentate, like since polydentate also include the tetradentate, here in, as here it is shown in equation 6.42. So such type of reactions occur, and a polydentate phosphine, here they are formed starting from a monomer. So in figure 6.28, a racemic tetraphosphine, here it is shown, and it is maybe better than conventional catalysts. So in figure 6.29, you can see a polydentate phosphine. Then coming to macrocyclic phosphine. So the phosphorus, only the where a number of macrocycles get attached. So along with the mixed sets of P and N. So these are examples of macrocyclic. So as the name implies, so many substituents are allowed for this type of macrocyclic phosphines. Then we have phosphide ligand. So when instead of R groups, OR groups are there, then it may result in ligands which are similar to phosphine ligands, such as POMe3 or RO2, POP, OR2. Then heterocyclic phosphorus ligands. Phosphabenzenes, they are popular heterocyclic phosphorus ligands. The phosphols that is represented in figure 6.31a, they simply behave as pi eta 1 donors, or their pi electron density it has involved, and they serve as mostly bridging ligands. So heterocyclic phosphorus ligands, they have been represented here in 6.31a b c. Then comes cyclometallic phosphine complexes. So the phosphine ligands, they were mostly engaged in proton transfer reactions to give MC bonds. And the reaction for such an example is given in equation 6.45. The formation of 4, 5 or 6 membered heterocyclic rings, it takes place when longer chains of alkyl phosphine, they lose either lose beta, gamma or their delta hydrogen atoms. And here in figure 6.32, the obtained products here they have been listed here. Then coming to dialkyl diaryl phosphidoligands. So here in equation 6.46 to 48, various important preparations of terminal or bridging complexes of R2P ligands are been shown. These complexes, they various, it mostly uses the cleavage method, and a variety of such complexes are known. So where these complexes, they are similar to dialkyl amido compounds. However, homoleptic complexes they are shown, and mostly what happens is phosphidoligands, they can be made in this way, that is represented in figure 5.63. Then phosphanidin ligands, the compounds with MPR units, they are generally, they act as transient intermediates. But compounds like this, they can be isolated where R is a bulky group. Usually the when the ER group, it serves as the bridge between mu, they are serve as the bridging compounds. Then the electronic requirements of the metal atoms, it decides the type of the bonding or that is reflected in their structure. So here various types of phosphanidin ligands have been shown in figure 6.34 and 35. Then the ligands with P double bond P, P double bond C, and P triple bond C have been shown in figure 6.36.
हेलो मैम मैम ए पीडीएफ गुडा कोठू पाई परिबो हमें
तमरा गोटे अछि ई ज्ञान कोश अछि वेबसाइट
को
एठी जो
वेबसाइट
ई ज्ञान कोश रे एगुडा सब अवेलेबल अछि ए जो तमरो जोठी तमे रजिस्टर करिछ तमे
आज्ञा
जतो बळकू तम पोर्टल रे लॉगिन करिवो हैला
हां हां
सेठी अछि दैट से लॉग से पोर्टल ता होची ई ज्ञान कोश हैला GYANKOSH ता भितरे तमे तमरो जीवो MCH-001 एटा ओके सेठी तमे देखिवो तमरो ए जो कोर्स कोड ता होची MCH-011 तो तमे जतो
सेटा जो
बळकू
माने जो हमरो इग्नो साइट ऑन करिया पड़ियो ना डायरेक्ट गूगल लो मारतले पळे आसियो
तमे जदि मते एइगुडा होची क्लास रे इंटरप्ट करी पचारिबो मोर तो कोर्स
सॉरी मैम
सरीबनी तमे एटा सुनो तमे जतो बळकू तमरो स्टूडेंट लॉगिन जतो बळकू पोर्टल खोलिबो सेठी
आज्ञा
देखिबो सेठी अछि तम कोर्स रे जहा तमरो को कोर्स अछि कोन अछि सेठी पूरा सब ए पीडीएफ पूरा अपलोड अछि और जदि तमरो किछि माने ए रिलेटेड किछि पचारिबार अछि तमे पाणिग्राही सान को बा तमरो जो सेंटर कोऑर्डिनेटर अछंती तांको डायरेक्टली पचार देबो से तुमको लिंक पठेई देबे सब ठीक अछि
ओके मैम
ओके
थैंक यू
So now coming to unit 7, this unit also deals with metal pi complexes. The first we have completed the metal pi complexes part 1 and this is metal pi complexes part 2. So here we'll be talking about metal pi complexes with alkene, alkyne, allyl and the most important is cyclopentadienyl ligands. So the different types of compounds that are observed in metal pi or pi donor complexes with alkene group. Here it has been shown in figure 7.1 ABC. So the alkenes, they may donate an even number of electrons to the metals like this, and allyl groups, it is also pi bonded where the allyl anion, it donates 4 electrons. Here it is shown in figure 7.2. The alkynes, they donate one pair of pi electrons or both pairs. Here it is shown in figure with the ligands, how they coordinate with the alkyne group, and the cyclopentadienyl group, that is the C5H5 ligand. It is actually eta5, that is pentaheptocyclopentadienyl group. It is an anion and it donates 6 pi electrons, as here it is shown here in figure 7.4, an example of a pentaheptocyclopentadienyl group, that is C5H5 group. Here it is shown. Benzene and its derivatives, they are known to donate 6 pi electrons and they have a hepticity like eta 6, and here it is shown here. Then eta 7, that is the hepticity is 7, they are quite known, and this is particularly for the tropylium ion, that is C7H7 plus, and this is represented here. Now coming to alkene complexes, so the interaction of ethene with a metal atom, here it has been shown in figure A. It indicates the donation of an electron from the filled pi molecular orbital of ethene to the vacant metal sigma orbital, and also the interaction of the ethene with metal is also possible by the acceptance of the electron density from the filled d pi orbital into the vacant pi star orbital of ethane. So if we look into the ethene complexes of d metals, then we see that there is a balance between the electron donor capacity and electron acceptor capacity, but the change of the extent of donation and back donation can be also be regulated. So the strength of the C double bond C bond will decrease if the pi bond increases. So now here in metal, the nature of this actually, when we decrease the strength of the C double bond C, and that further increases the pi back bonding, this nature of reversal of the ethene reactivity is called as its Umpolong character. Now, particularly in dihaptoalkynes, the substituents, they bend away little from the metal atom, even if there is a small degree of back bonding from the metal. Also, the C double bond C, it has a slightly greater character than that of present in the free alkene. So as a result of this, if there are any other groups which are present and they sterically force the substituents, so this situation also arises and the electron density moves away. Now coming to preparation of alkene complexes, first is by direct reaction. So these are the cases when unsaturated metal complexes may react directly with alkenes. This is called as, for example, the Vasquez complex. It reacts ethylene with iridium ClCO PPH3 to form the Vasquez complex. Now, many other metal atoms, they directly react with alkenes and particularly dienes, producing the metal pi donor complexes. And one other example, it has been shown in figure 7.8. Then comes the displacement of a weakly bound ligand. Suppose we have a very weakly bound ligand to a certain metal atom, then displacement occurs, and this is also one method of formation of your alkene complexes. Then is reductive addition. It is actually the most popular method for with platinum group metals. So here, as it is shown in equation 7.6, a higher valent metal of the metal with reacts with the alkene complex or with the zero metal. First, ethylene is taken, the higher oxidation state of the metal salt is taken, and it reacts with the zero valent metal, and it finally forms the ethyl alkene complex. Then alkyne complex. Now broadly, alkyne complexes, they have been prepared similar to those used for alkene. So but alkynes, they are more electronegative in nature, and so they bind more strongly, and thus the back donation here is better. So also regarding the synthesis, the following methods have been used. So monoalkynes, they can function as 4 electron donors by utilizing the pi bonds here as it is shown here. Unless there are any bulky substituent groups or steric hindrance that interrupt with the metal, alkyne complexes with divalent platinum group metals, they are mostly unstable in nature and they give rise to a variety of other products. So like here, if we look into equation 7.8i, A2IN2, we can see how the unstable, the platinum, here these complexes, they are unstable and ultimately they decompose to form a variety of products. So in also alkyne polymerization has been observed, and such polymeric alkyne compounds have been isolated, and here some of the examples have been listed below. Now coming to allyl complexes, the allyl ligand, that is CH2 double bond CH, CH2 minus, it binds to metal in basically two configurations. So the first is a 2 electron donor with a single negative charge, and this here it is shown in figure 7.10. And in the second case, the allyl ligand, it behaves as a eta 3 ligand here as it is shown in figure 7.11 in this case. So here in A, and then this is both are resonating structures. So thus the allyl complex, the allyl ligand, it can actually exist in two configurations, bridge with the metal atom in two configurations. The allyl ligand, it donates 4 electrons and it has a mono-negative charge. So but in actually the allyl ligand, it has a symmetrical value as it's shown in figure 7.12. This is the actual representation of a allyl ligand, where the curved line, this curved line, it represents all the bonding electrons. So a better understanding of the allyl group has been done with by considering the molecular orbitals here as it is shown in figure 7.13. The molecular orbitals are also shown to understand the particular stability of the allyl group. Then coming to cyclopentadienyl complexes. The cyclopenta, these are basically formed by C5H5 minus and the related and such molecules. So these are some of the metallocene that are formed by cyclopentadienyl complexes. So here we can see this is dicyclopentadienyl titanium. This complex, it is dark in color and it actually exists in the form of this. These are some of the properties of the commonly occurring metallocenes. Now, cyclopentadiene, that is C5H6, it forms the cyclopentadienyl anion, that is C5H5 minus, by simple deprotonation in acidic conditions, by simple deprotonation method. So this anion, it is a mildly acidic hydrocarbon. The aromaticity in it is because due to the 6 electrons in its pi system. So the delocalized 6 electrons, they form a ring that leading to 5 bonds that are of equal length. So the cyclopentadienyl, it may be monohapto like eta1, trihapto, allyl, pentahapto, which is called as cyclopentadienyl. Also there are complexes of monohapto cyclopentadienyl group. So mostly this cyclopentadienyl is treated as a 6 electron donor. So here if you look at the molecular orbitals at figure 7.15, we can see that the electron donation to the metal, it comes from the field 1 pi, that is the sigma bonding and pi bonding MOs, and the sigma back bonding, it comes from the dxy and dx square orbitals here as it is shown. Now the synthesis and properties, the metallocenes, they are usually symmetrical metal compounds, that is the bis cyclopentadienyl metal complexes. First, the parent diene, that is C5H6, is prepared by thermally cracking dicyclopentadiene. So prepare this cyclopentadienyl ligand. We first start with the thermal breakdown or of dicyclopentadiene. Here, thermal decomposition cracking is done as shown in equation 7.11. Then by removing the H plus from the diene, the synthesis is followed. So here the removal of H plus, here it is done in sodium, either in sodium in THF or in Tl2SO4 in KOH. So then and finally the anion is here, it is obtained. So the isolation of C5H5 minus is very difficult because they are not stable in water. So they can be used for the direct reaction with the metal to form the desired metallocene. So another a hydrated salt is also used. So that is to form the in situ preparation. Like in equation here, table 7.1, it shows a general method of, it shows the various methods of preparation of the common metallocenes. Now here in equation 7.15, the preparation of an unusual metallocene with iron, here in equation 7.5 it is shown. Also a number of mixed sandwich compounds are known. For example, isoelectronic series, they have members whose methods of synthesis show the development of organometallic chemistry like this. So here in figure 7.16, an isoelectronic series, if you look into this, of mixed sandwich compounds of metallocenes have been reported. So if we take the example of cyclopentadienyl, benzene and manganese, particular this in that is shown in figure 7.15b, its synthesis is actually done from C5H5 MnCl and PHMgBr in THF as it is shown in this equation 7.6. The intermediate is then converted to the pi benzene complex, and following which the metal is reduced. So Zeiss, he studied this type of reactions using dibenzene chromium, which is represented in figure 7.16a. Then coming to preparation of molybdenosine. Molybdenosine, it can be prepared by the reaction here as shown in equation 7.18 and 7.9. Molybdenosine, it reacts with the exception of ferrocene. The sum of the common reactions here, it has been given in equation 7.23 and 7.25. Then the structure and bonding in metallocene. So we here in figure 7.17, the structure of ferrocene and ruthenosine, they have been indicated. The geometry of particularly cyclopentadienyl rings, they are different in solid state. For ferrocene, in like here, if you look into this, it is staggered and the symmetry is D5D. But for ruthenosine, that is here in this figure, and osmosine, they are eclipsed geometry and they have a D5H the symmetry. So thus we can see that the geometry, they are different for the different types of metal active in different metallocene. Now here, that ferrocene and its derivative, they have free rotation rings. Particularly for ferrocene, if we look into this, they have free rotational rings, but in solid state crystal packing. But when we consider in solid state, the crystal packing, here it comes to play. So here, if in the gas phase, the barrier of, particularly when we take in the gas phase, the barrier for ferrocene rings is very less. So here certain reactions have been performed, and the bonding of metallocenes was understood from their electrochemical properties. Like here ferrocene, it gives deep.
Hello, ma'am. Hello.
Low temperatures, a solid dioxygen adduct, here it is shown in figure 7.1b. It is obtained from the purple metallocene by absorption of oxygen. So ferrocene, it is a perfect example of metal binding to pi donor ligands. And here the atomic orbitals of ferrocene has been shown in figure 7.19. The geometry, the symmetry, it has been represented here in figure 7.20. And the qualitative MO diagram of ferrocene has been shown in figure 7.1. So in 7.21, the MOs, they are ordered as per the, here the MOs in 7.21, the MOs, they are placed according to the latest calculations. According to, as per the calculations, it has been found that the metal dzx and dyz orbitals, they interact more strongly with the cyclopentadienyl than all these characters. So the actually this is a very complex, the understanding of the MO of ferrocene is a bit difficult task. So we need to consider all the primary orbitals starting from the ground level to the A1G, the E1G, and all other orbitals. The metallocenes, they with only partially E2G and A1G MOs, they add extra ligands. Now we all know about the Wilkinson catalyst. So the Wilkinson, he tried to prepare a cyclopentadienyl sandwich of rhenium by a reaction of ReCl5 and NaC5H5 in THF. So previously it was expected that the product would be rhenium C5H5. However, the molecule was and it was found to be diamagnetic in nature, and its proton spectrum, it consisted of a doublet. So from looking at the proton spectrum and other studies, the formula of the compound was found to be this, and ultimately this is the arrangement that was found from the study. The cyclopentadienyl of rhenium was found to be this. So thus the type of the nature of the central metal atom, the number of the cyclopentadienyl rings, they affect the tilting of the arrangement of the cyclopentadienyl rings and subsequently the geometry. Here the in figure 7.23, the contour diagrams have been shown for bonding orbitals obtained for C5H5 rings when they are tilted from their positions. So here a qualitative MO has been shown for bent metallocene. So and titanosine and manganosine have been shown here in figure 7.26 and 7.27. These are also very interesting metallocenes. The titanosine, that is C5H5 hold to titanium, that is, it was formed by reduction of this compound, and the molecule was later confirmed to be a dimer, and this is the structure that is obtained for titanosine. Now preparation of manganosine, here it is done with Na plus C5H5 minus with manganese chloride in THF, and here in figure 7.28, the structure or the compounds with cyclopentadienyl groups, they have been shown here. Various examples have been shown. So now coming to borazine, the reaction of ammonia with diborane, it gives a compound B3N3H6 known as borazine, and here it is shown in equation 7.29. Borazine is prepared by reducing trichloroborazine with sodium borohydride. It is first prepared with BCl3 plus NH4Cl, and it follows the reaction. Some common comparison of physical properties of borazine and benzene, it has been shown here. Borazine, it has a regular plain hexagonal structure. The B-N bond distance is found to be 144 pm in borazine, and it is actually much less than a single covalent radii of B and N. So this is valence bond structures of borazine. It has been represented here. The molecular orbital calculations, it is not included, and many experiments have suggested the reactions of water with HCl with borazine, and a few of this has been of borazines are mostly the sign the boron, in particularly in borazines, the boron, it undergoes a nucleophilic attack, and this results the nitrogen atoms are here in borazine, they are relatively negative, that is they are considered with a delta negative charge. So with this, the borazine part is completed. In next class, we'll start with arenes and other alicyclic compounds.